Hey, it's Mrs. Moret here with today's homework. So we had Unit 5, Lesson 8, Practice Problems, page 340, numbers 1 through 6. Our big idea today was scaling the outputs of a function to create a new function. And on number 1 here on your assignment, we can see that that's what's been done to all of these graphs because they have the same x-intercepts. So when they have the same x-intercepts, you can always write one function in terms of the other using some sort of scale factor, and we call that scale factor k. So it says in each pair of graphs shown here, the values of function g are the values of function f multiplied by a scale factor. So for each of these, we are starting with the dashed function and trying to write a rule for the solid function. And to do that, we look at the pair of coordinates that we know. So these have the same x value. And what's the only thing that's been changed is the y value. And so the negative 121 has been multiplied by something to get negative 55. And so to figure out what that is, you can write a simple equation. Negative 121, let's see here. Move that over, there we go. Negative 121 times some value k is equal to negative 55. So that's the y value from our original function times a scale factor is equal to the y value of our new function. And so we just have to divide by negative 121 to figure out what that is. And we get positive 55 over 121. Those numbers can both be divided by 11, and so this fraction reduces to 5/11. And so then to write g in terms of f using function notation, we would say g of x equals 5/11 times f of x. You can put a little time symbol there if you want to. You don't have to. And that's how you do it. So on the next one, again, we're starting with the dashed and trying to write a function rule for the solid. So number 1, I expected my value to be less than 1 because that would be a vertical compression. Number 2, I'm expecting this value to be more than 1 because it's a vertical stretch. I can see that just by the way the graph looks. Also, for any value of x, I know like this is a greater number than the corresponding one below it. On the negative side, you could say like, oh, it's more negative than the corresponding number that goes with it. So for this one, we have negative 8. We multiply it by something to get negative 13.6. So negative 8 times k is equal to negative 13.6. So divide. And let's see here. Negative 13.6 divided by negative 8 is equal to 1.7. So that means that g of x is equal to 1.7 f of x. All right, so each of the outputs is being multiplied by 1.7 to get the function g. Okay, this next one, I'm going to expect it to be a vertical compression because we can see like the solid graph is much lower than the dashed graph. And so when we look at our corresponding points here, it's giving us when x is 0, f of x is negative 50, and g of x is negative 12.5. So that tells me negative 50 times some value k is equal to negative 12.5. And so we're going to divide by negative 50. And let's see here. Negative 12.5 divided by negative 50 is 0.25. So g of x is equal to 0.25 f of x. And then the last one here, starting with the dashed line to get to the solid line, I can see there's a reflection. And then this isn't as steep as this, so a vertical compression as well. And so let's see here, our corresponding points are 6, 6 on f of x and 6, negative 1.5 on g of x. So 6 times some value is equal to negative 1.5. So 6k is equal to negative 1.5. So divide by 6. So negative 1.5 divided by 6 is negative 0.25. All right, so this time g of x is equal to negative 0.25 f of x. All right, let's look at the next page. Number 2. So number 2, will scaling the outputs of f change the x-intercepts? So the x-intercepts here, there's 1, oh, just 2 of them. I think that's like a little bounce right there. There's just 2 of them. So at those points, the output is equal to 0. So if you multiply 0 by a number, your answer is still going to be 0. So it's not going to change the x-intercept. So this is a no. And then part B, will scaling the outputs of f change the y-intercept? Well, the y-intercept is somewhere around, I'd say it's about 3. And so if I multiply 3 by any number besides 1, it's going to equal something else. So it will change the y-intercept. So this one is a yes. Okay, number 3, we have a little controversy about f of x versus g of x. So the function for g of x, 4 times 2 to the x. So we have 2 ideas about this function compared to this one. So Chiron says the graph is a vertical scaling of the graph of f, and Mai says that the graph is a horizontal shift of the graph of f. Do you agree with either of them? So for 2 to the x versus 4 times 2 to the x, could we say this is a vertical scaling? And I would say absolutely. If g of x is equal to 4 times 2 to the x, oh, and this is Chiron's idea. If we say g of x is equal to 4 times 2 to the x, then all of the outputs are being multiplied by this 4 here. So definitely a vertical scaling. I agree with Chiron. And then at first I didn't agree with Mai, but then I thought about it some more. And so let's see here. Mai says the graph is a horizontal shift of the graph of f. So could this be a horizontal shift? And this is Mai's idea. So if we think about this 4 times 2 to the x, well, 4 is a power of 2. So I could rewrite the 4 as 2 to the second times 2 to the x. And then when you multiply together powers with the same base, you add their exponents. So this is equivalent to what we started with, and then it's also equivalent to this. They have the same base of 2. And so I'm just going to add the exponents together. When you add 2 and x, you get x plus 2. So if we do some work to the equation, they're totally equivalent, and this actually does have a horizontal shift to the left 2 places. Okay, so actually agree with both. Okay, smart kids get a smiley face. All right. Let's see here. 4, 5, and 6. We're almost done. Number 4 says the dash function is the graph of f, the solid is the graph of g, express g in terms of f. So all I see for this is just a reflection over the x-axis. So when you reflect over the x-axis, you are changing the outputs. You're making the outputs negative. And so that tells me that g of x is equal to negative f of x. Okay, again, the outputs are what's changing on this graph. Next, this is a table for an odd function. So in an odd function, opposite inputs have opposite outputs. So I'm just going to use that strategy to fill in. So here, when x is -4, this is -3. So +4 would be its opposite input. Opposite output is +3. If this is -11, down here it's +11. If this is +5, up here it's -5. And then 19 here makes this one -19. And then that's all the way filled in. And then finally, number 6, the graph of f of x is x to the third. So that's going to be the dashed graph. And a graph of g, which is a transformation of f. Write an equation for the function g. So I can see it doesn't look like it's been scaled at all. It just looks like we're moving kind of that little point where the function turns down 4 places and to the left 1, from 0 to -1. So down 4 and left 1. So using just function notation, I would say g of x is equal to f of 1 to the left is going to be x plus 1 inside the parentheses. And then down 4 would be -4 on the outside of the parentheses. So that would be in function notation, but it does say to write an equation. So what I know is the original function is just x to the third. So that tells us g of x is equal to x plus 1 to the third. So that shifts the function 1 to the left. And then -4 out here, and that shifts the function down. So this is the final answer because it does ask for an equation rather than function notation. All right, that is the end of your assignment. I hope you found this helpful.